hours restriction.
Oh, okay. Want to talk just about the student fee distribution. Now, we can talk about the actual probability density function being made of their gamma functions, and I don't think this is necessary because as I understand, your calculators have the ability to do an inverse on the student fee.
Mm-hmm.
Is that right? Make sure everybody can do this. I suppose we can do one of these, and actually, let me see if I can get this real quick. But I just want to make sure we can all do these things. I'm not going to, on the quiz today, there's not going to be that student fee distribution, but on the final, or I should say, on the next quizzes and stuff, I could ask a question on that. I haven't decided yet. And I want to make sure everybody's calculator can do this without any problem. And just briefly, why is the student fee distribution important? Anybody, in your own words?
It's for small sample sizes.
That's right. Small sample sizes that, in the limit, as the sample size gets larger, becomes Gaussian. So this is called the fat tail, I think, in some places. And the weird thing about that is it came about because the guy at Guinness Beard needed a way to use smaller samples for actually yeast and other things to figure out the alcohol content and other, I guess, other quality factors. But it was weird because of all the places you expect mathematics to be used, the breweries the last.
I think it's always funny when like Euler will come up again in something like accounting too. It's like, hey, I know that guy. Yeah.
I'm trying to convince Jay to get his face tattooed on him. Really? I mean, so it's either do like a transcript kind of thing.
Do you have to wear a mask during like a test so people can't use like an equation sheet?
No, he only has his face though, not the actual.
Oh, like the guy.
Yeah, the guy.
Oh.
Yeah, the guy. So a math tattoo would be hard though.
You just tattoo like all the equations you need for the semester, like on your arm.
For me, it'll be hard because I'm passing that.
All right, we'll do 4-5.1. And the only reason I'm going to do it with 9 coils is because I want to make sure, now I'm not, because I don't know how your calculators work. I don't know if you put in the number of samples or degrees of freedom.
Degrees of freedom.
Is it degrees of freedom? Okay. And that's one, the number of samples minus 1, I believe. Okay, so for this one, let's see here.
You said degrees of freedom is number of samples minus 1.
Yeah, and it should be in there. I'll tell you where it is if you want to write it down. Well, it's on page 170, but if there's 8 degrees of freedom, it would be 8 minus 1, 7 would be, I mean, sorry. If there were 8 samples, 8 minus 1, it's going to be 7, that would be the number of degrees of freedom. Now, something about that, I didn't get into why they call it the degrees of freedom, but in general, like, you had dynamics, right? Have you had statistics, dynamics, the strength of materials? All right, if you have 1 degree of freedom, a thing can move in one direction.
Mm-hmm.
2 degrees of freedom, like in X and Y axis, 3 degrees, X, Y, Z. 4 degrees, it can move in all those axes plus rotational on one. 5 degrees, it would be rotational on 2. 6 degrees, it's going to be something where another orthogonal axis, that'd be 6 degrees of rotation. That's for like rotational energy. After you get from that point on, now you're taking a look at second order effects, and that would have to do with like orbital stuff, where now the thing's in motion as well, and it gets further and further from into an abstract concept. This, I don't know why you use degrees of freedom for this, this particular student T distribution, because there is no motion of the vat stuff to speak of, but it works, so that's the only thing that matters. So anyway, for this one, he says he has N is equal to 9 samples, right? And what else? Give me the specifics.
Claim to have a mean resistance of 100.
Okay, R bar, 100 ohms, go ahead.
Sample mean is 115.
All right. Oh, all right, so R bar sample is 115, go ahead.
And the sample standard deviation is 20.
All right, so this is the sample standard deviation is 20. Now, the way I do these things, I start with a density function, and this is, this would be a two-sided. Did you follow me on this? It's gonna, because you're talking about how far you depart from the mean value. Now, how much, if you're not just greater than or equal to. So I like doing this. I always start and I say, and you can do it the way he does it in the book, which is a little different. For this would be the density function, it would be student T, so it would be FT of T. And here is going to be the mean value, which is 100. And the student T looks like this. And what he wants, the actual claim is that the resistance that he has is 100 ohms. And what's the standard deviation? Does he ask for about the confidence interval?
Yeah.
All right, so what is A?
Is the claim justified if the 95% confidence level is used?
All right, so we want a Q of 95%. So getting back to that thing, this is his claim with me, so I'm just going to draw it up. That means the area here is 0.95 would be the area associated with that. This is the claim. And now we're going to figure out what this value is, what this value is, right? Now, you can do this a couple of different ways. I don't know if your calculators have a way to doing an inverse and actually saying two side, one side. Doesn't matter. We're going to go ahead and do this. Well, I should ask you this. Have you all tried this kind of stuff on your calculator, the student T, or not? Has anybody? One, maybe?
I tried it, but I can figure out like how to do the gamma functions.
No, you don't need gamma functions. Your calculator is, what kind do you have?
Inspire.
How many have the Inspire? Doesn't that do the inverse student T, student T, student T? So we should be able to do it, but I want to make sure everybody can understand how to do it. And since you have calculators and I don't, you'll tell me. But anyway, remember how we did this before? If it was what? If it was the Gaussian, what did we do? Well, you know, if you want the 95% confidence interval, ultimately, what you want to say is this. I mean, you could look up the value of K for this, but how can we get it a different way? All right, let me try this. You know, the total area is 1, right?
Mm-hmm.
And if I look at this, I'm after the lower and upper limits here, but I know if there's 95% here, this tail has 5%, and this tail has 5% because of symmetry. Do you all agree with that?
2.5% or 5%?
Or I'm sorry, 2.5, my bad. 2.5 and 2.5. You're right. Is everybody with me on this? Now this is one way to do it. If I take a look at that, and I want this value right here, that's the one I want, then I can say that really that value would be equal to the cumulative, and I'm going to do it, the cumulative density function of, and I'll just call this Z critical here, of Z critical would be equal to 0.95 plus 0.25. You all follow me? Because you're saying all the area up to this point would be equal to that. That would be your cumulative density function starting at minus infinity. Is everybody with me on this, class? So if you did this with the Gaussian, the cumulative density function, cumulative density with the normal distribution, in MATLAB you put in the distribution. If you want student t, Poisson, Gaussian, and it will give you the inverse. Because I was playing with that in MATLAB, but in your calculus I'm not sure. So if you did this one, and this is going to be 0. And this is going to be 975. The value of x, just do me this favor. Get this if we assume Gaussian. It's not Gaussian, but if you assume Gaussian, what do you get for that? And I'm trying to make my point where you can see the logical order of how we're going to change up the student t. And by the way, this will help you on the quiz anyway.
1.96.
Anybody confirm that? Class? You get that? For Gaussian, inverse Gaussian, right? You all know how to do that in your calculus. This I'm going to be sure, right? Okay, fine. That's Gaussian. Keeping it with the Gaussian. If it was Gaussian, then we'd say this 1.96 right here would be equal to the actual value. This would be for, if we were calculating the value of z critical, I should say, it would go actually right here. I put z critical here. That's not exactly true. Maybe it should be an x here. Well, actually, it is called z critical in the book, but I'm going to use this as the value of r. Maybe I'll call it r critical. No, this would be, bad on this one. The book calls this z critical, and that z critical here is actually equal to the value of x that I want. This would be the upper limit. Call it x, or r critical, better yet, r critical. So this is going to be r critical minus r bar, and then it's over the standard deviation divided by the square root of n. Just bear with me on this, I'll put in the values. But everybody understand the logic? This is something you probably know very well, right? So we had Gaussian. Sorry. If we had Gaussian and we wanted the critical value, it would be 1.96 times the standard deviation, which is, of the sample is 20, is that right? 20 divided by the square root, and we had 9 samples. And it's going to be that plus r bar, which is 100. And even though this is completely incorrect, because there's only 9 samples, what would the value be, just to make sure everybody knows how to do this? We're assuming Gaussian, it's not Gaussian. We're going to go the same route. We're going to do student t, same exact thing.
I got 113.1.
Anybody else? You got 113.1? All right. So this is 113.1, and because this is the critical value, right? So if I take 100 minus that, what do you get down here? That's
86.93.
86.93 ohms, okay. Now, if the actual measurements of the mean are anywhere between those 2 points, the claim's verified, all right? This one's 115, and it's not, but it's Gaussian. You all follow me on this? Now we're gonna do the same thing, only now we use student t. So, yes, sir.
So that distribution is centered about the claimed mean?
No, the actual mean. It's the mean. The claim, sorry, you're right. The claim mean is 100 ohms, and if we have 95% confidence in that, if that's the claim, you need to know the lower and upper limit. This is how I do it. I know they use a different route, but it's much easier for me I think it's much easier to see. This is what's claimed. Once you have that, does the measurement fall within or not? And that's what it comes down to. So his means 115 is beyond that. It's not justified by 95, maybe 97, maybe 98. You all follow me, class? Anyway, now going back to student T, here's where I need you to help. So for student T, I'm going to do the same thing, only instead of this, I need to, what do you call this thing, the cumulative T distribution or something like that? And for the cumulative T distribution, I'm assuming your calculators are saying cumulative T distribution, I should say T distribution of, call it Z, or he uses cap T, I think, here, is actually equal to the integral, I'm calling from minus infinity to this value T of the density function of student T dt. Now, remember, this density function is the one with the gamma functions. Y'all follow me, class? But do you have something like this in your calculator?
I've got lower bound, upper bound, and then degrees of freedom.
All right. Well, the degrees of freedom, this one has 9 samples, so the V would be 8 in this one, the degrees of freedom. Y'all with me? Just work with me on this one. Make sure your calculators can do this, because I'm only going to go over this a little bit today. And it should be a natural extension of what you've been doing with the Gaussian. But I have to make sure you know how to do this thing in your calculators. Y'all with me? Now, you can put the lower limit as minus infinity, and you can put the upper limit as something unknown that we want to calculate, right? So here, and it's going to be 97.5%. Y'all follow me? Just like before. And that's the entire area up to this point. This is the way I'm doing it. Y'all with me on this? The book might do it a little differently, but that's the way. Everybody with me on this? All right, now tell me, with the student T distribution, what this value is. And I'm calling it Z critical. I have the answer, but I want to make sure you guys.
I don't know if mine's right. I got 2.31.
I think it's 2.306 actually, but
Yeah.
2.31 is fine. 2.306?
Mm-hmm.
Okay. If that's the value of Z critical, it's just the same as before. I'm trying to calculate the bounds to see where the limits are when we say 95% confidence. And for that, I know that that's equal to, and I'll just do it this way, R, and this is R critical, and it's really minus or plus R bar over the standard deviation here divided by square root of n. As before, you can see the real thing is I need to take the standard deviation, well, I'll go ahead and write it down. For the upper limits, because that's what we're going to be after, or I should say for the upper limit RC, it's going to be equal to 2.306. Remember for the prior one, for Gaussian, that was 1.96. So it's getting wider, you might say, or that number's bigger. And then it's going to be times S, which is 20. And this is over square root of 9, not 8. It's going to be that plus 100 ohms. But this is the critical value. So if you get that and add it to 100, what do you get up here?
115.373.
Anybody confirm that?
Yes.
Everybody know how to do this on your calculators. This is the critical thing. With me on this, class? Because it's the same process, except using the cumulative distribution function. Now you use the cumulative student T, whatever they call it. What do you call it in your calculators?
TCF, EPF.
TCF?
TCF, yeah.
Oh, TCF, okay. Now, if you happen to use MATLAB, and I doubt you will, but in other courses you might, MATLAB has all these inverse functions. You have to put in the degrees of freedom, you're right, degrees of freedom, you have to put in the mean value, and then it's either going to be the inverse or it's going to be actually calculating the percentage, but it'll do it. And you can put it, like if you have, if you want these bounds, upper and lower, actually, I'm not sure about that on your calculators, if you can do that easily. I know like in the book, he has it listed for 90%, 95%, basically the value of K. I think 97.5, I'm not sure, or 97, something like that. But I don't think he has the values for the student fee. Maybe I missed it. But this is the way you do that, and that's 115. So now we see, is this within 115 class?
Mm-hmm.
And that barely, right? Just barely. So I guess what I'm really trying to say is the student T replicates all the steps. The only thing different is the cumulative function, distribution function is different for student T than is for Gaussian. That's it, in a nutshell. Now, if a good question that you should at least ponder, if I asked the question, what would the confidence intervals be using student T for this value, how would you get it? Now, better yet, let's not go that close. Let's say it was 120. How would you get it? You work backwards, don't you? In reverse. So if this was 120 here, that would be over here, right? We don't know this value. You with me on this one, Ken? We know everything else, and we just work backwards and get the value of the confidence interval, because we're going to get this value again. We're going in reverse. You follow me? And you would get this value, then you'd plug it into your calculator to see where, in fact, what confidence interval it is. Fair enough? So make sure with these problems you can work forward and backward. You can find the confidence interval. If it's not specified, then we'll allow values, or you can figure out if values are within a confidence interval. That's the whole idea for student T and for Gaussian, or cumulative distribution function. Fair? Any questions on this? I want you to be at least, because I wouldn't ask, I'd give you tables normally, but since I think, does everybody have a calculator that can do this in here? If you don't, let me know now, and I'll provide you tables. But I want to make absolutely certain, if you get a problem like this on the final or in a quiz, you're not going to panic. So you can see exactly how to do it. Now, that said, by the way, you've heard about this, what is it? Psoriasis, this food poisoning, or this, in all the lettuce, and apparently it's in lettuce from one supplier. This is what I've seen, and there were yesterday 10 confirmed cases in Alabama. The upshot of the whole thing is, don't go out and eat fast food with anything that has raw lettuce and stuff like that in it, because, or just buy whole lettuce if you're going to buy it. You all know what I'm talking about, don't you? Everybody? Anybody here ever get food poisoning? Well, I have, from a deer sausage that wasn't cooked at a high enough temperature. That's as sick as I've ever been, man. Thrown up, diarrhea. Basically, you had to get better to die. And you don't ever want it, I'll tell you that much. There's only one Chipotle's around here, right?
There's two.
I mean, is there another one downtown, or is it just in Opelika?
There's one. Wait, you said
There's one in
There's
Opelika?
one down, yeah, there's one over in.
There's
You said Chipotle?
Oh, yeah, and then there's something like right across the street right there.
There's one by Chick-fil-A right over there, but is there another one down?
Oh, yeah, there's one down.
All right, just watch out for stuff. It's my own thing I'm gonna do is caution you. I'm not gonna tell you what to do. several years ago, Chipotle had another food poisoning problem. I don't remember what it was, but a lot of people got sick. And I don't know if they got sick here or not. I don't eat there, but anyway, that's the fact. So now we're going to go into chapter 6. And here it becomes, now this is getting a little deeper theoretically, and it'll get, in a couple lectures, a lot more complicated, or at least, if you don't spend time with this stuff, you get totally lost. So this is going to be autocorrelation functions, spectral energy density. This is chapter 6, and I'm trying to give you the easy way to figure out this stuff. We'll do problems. So with autocorrelation functions, normally if you have some function x of t here, and x of t is a random variable. Now, there's a couple of things you have to understand. Before, if we had a value of x, this is important to think about, because this is going to be about how you define ergodic versus non-ergodic systems. So if you had a value of x, you had a probability density function, and all the statistics were specified from that. You got everything. You can get the mean value, you can get the mean squared value, you can get the standard deviation of x, you can, or I should say the variance, all those things can be easily identified if you have the density function. You'll notice this is not a function of time. This is a real important point. It's just a function of x. But when you have x that's a function of time, and I want you to listen to this so you don't forget this, then if I say I have a process, and this is x that's a function of time, and it's doing this, each value of these x's, if I take x of t1 here, and there's another x of t2, these values can potentially have different probability density functions. Let me give you an idea of this, something that would. You know, the Earth rotates every 24 hours. So if you talk about the ion density or electron density in the atmosphere at 100 kilometers above Auburn, Alabama, and you map that, you're going to find the ion density is going to have variation statistically, but the nighttime density is much, much less than the daytime because of sunlight. It means that even though at x1 of t, there is going to be a random, you would have a density function that would describe that. This gets into something, and you have to take moments of this in plasma physics and stuff. But this value has a different set of statistics than this value. You all with me on this? So that means the time average statistics, if we went and we calculated the average value over a 24-hour period of this x of t, it will be different than the average value as if, you know, over here, if we wanted this value, we'd calculate normally from minus infinity to infinity of f of x right here, and then it's going to be times x dx. Now that is spatial, or I should say it's one-dimensional. There is no time in that. You with me? But if this average value would be the same as taking the average value of the time domain, then it's called ergodic. And the term that they use to describe this is called wide sense stationary. Have you heard this? Anyone? For me? All right. It's very important. Now, wide sense stationary signals over a certain length of time happen all the time. We can say very easily that if we talk about just the thermal noise in a transistor or something, you've heard of thermal noise? The statistics of that are wide sense stationary or ergodic. They do not vary. I mean, if it reaches an operating temperature, they're not going to vary over time. You all with me on this? But if you talk about something, anything that's got periodicity, like, you know, the ion density at a given point above Auburn, Alabama in the ionosphere, because we know that there's motion, you can't assume ergodic, which means I can't say if I take a time, if I get, when I was at Penn State, I was in space science labs, and what they do is they record all sorts of measurements in the atmosphere over periods of time. They'd fire rockets up there, all sorts of stuff, and they'd get values of electric field, ion densities, all sorts of stuff. And what they like to do is just have that time record and then go with a computer, calculate the average, the standard deviation, the mean square value, anything that would be of interest. Follow me on this, class? And they can get statistics, you know, all sorts of information about this, about the mean energy and all that stuff. But if it's not ergodic, or basically wide sense stationary, those things vary with time, you can't do that. So that's why it's so important. And it's much easier to use time statistics to actually get the, like, look, can you all calculate the mean value for a 24-hour period if you had x of t? Yeah, right. You're just going to take that, integrate it over the entire time period, divide by 24, that would be the average value. You agree with that, class? Now you'll notice I didn't use a density function. What if you want the mean square value? You would take this, square it, integrate it over a 24-hour period, right? And then you would divide that by t, or by 24 hours. That'd be the mean square. From that, you could get the variance. It's very easy to do that if it's ergodic or wide sense stationary. If it's not, you're out of luck. And there are things, the physics world has a lot of these things to worry about. I don't worry about it so much because all the stuff I do is short period of time, type of stuff with radar. I don't have exposure for 3 years or something to worry about. If what I'm seeing is going to have the same density functions 3 years later from the time they start. So that's the deal with this thing. Now, when we talk about autocorrelation functions, usually they assume wide sense stationary signals. That's all, and you'll see this. So, but they don't always say that. And they start by saying if we have a process x of t, and we want the autocorrelation, I better show you this. I didn't talk about this yet. But if this is t, and this is the function x of t, I had this up there, right there, and I have this function as such, and I want the autocorrelation. Now listen, normally what they do is this. They're just going to say, there's going to be some t1 and some t2 here. Just two values. And there'll be an x of t1, and there'll be an x of t2. That's simple. Now, if you have x of t and you want the autocorrelation of this, it's normally shown as rx, and sometimes they'll have xx. It doesn't really matter, because if you're going to have what's called a cross-correlation function, you'll have x and then there'll be like a y here. But this is rxx, typically just r of x, and it would be t1 comma t2, and that is going to be the expected value of x of t1 times x of t2. Are you all with me on that? Now, typically what they're going to, well, t1 and t2, if they're a constant value, then you're really talking about x would have a density, x at t1 would have a density function, x at t2 would have a density function, right? But the way that's normally written is this. And I've got to make sure about one thing. Is, matter of fact, I think what I may do for the sake of time, I'm going to put up the PowerPoint and then I'm going to just do some problems to show you. But this stuff, you know, one of the things you're always going to wonder about, well, so what? That right there, you can get, if you have a data record, you can get this, and you're going to see in a second how you can get it. And if you can get that, you can get an enormous amount of information statistically, and you can look at the spectral density, the energy density of a waveform. But let me take care of this. I don't mean to be jumping around that much, but I was thinking about the best way to do this, and I just looked at my watch. I realized that time was of essence right there. This, by the way, you should have access to chapter 6. Do you all have that?
Mm-hmm.
What does that say? Import. All right, got a bad feeling. I better change the screen. Come on.
Did you hit the button on the desk for the thing?
All right. Okay. Thank you. Let me get back to this. Can you all see that? Everybody see it okay? All right, basically, we're talking about random variables, and I made it a point to talk about a wide sense stationary signal is really what this is applicable for. So anyway, if we have two variables, x1 and x2 of t, the expected value of x of t1, x of t2 is called the autocorrelation function. That I said. Moving on. If you take a look at this, this is a data record. You all see this, class? If you take a look at this, and you look at the actual autocorrelation function, he has a function of tau, and tau is just t2 minus t1. Now, you'll see how this works. You'll always see that the autocorrelation function is going to have a b. That would be a peak. That would be the expected value of just x squared. Follow me? That is like the RMS, or I should say the mean squared value would be right there. Follow me on this, class? It would be the statistical average of just x squared. And if you take a look here, what he's doing is he's saying, you see how jumpy this data is? It changes very rapidly. Like the value at, say, 250 is probably much different than 252. Whenever it jumps that much and there's not a correlation, a relationship between another, you get 0 for that, the expected value of those two multiplied together. But the slower things change, or the more, I call these things, the lower the frequency component, then you'll start to see a broadening of the autocorrelation function around 0, but they always plot it tau equals t1 minus t2 or t2 minus t1. Hear me now on this one. There's a couple things that are real important to observe. First of all, an autocorrelation function, for a legitimate autocorrelation function, it's always symmetric. It's always an even function. That's important. The second thing is that the peak value is always at 0. Now, it may have multiple peaks, but at least one of them, the peak of the peaks, will be at 0. That's an important thing. Another thing you're going to see, these are properties, they will not have any sharp, they will not have anything that's going to be a discontinuity except at 0, and I'll explain that. You can have an impulse function, but, and the best way to see this is just, I'm going to keep moving through here. So an example. Now here, if you take a look at this, x of t just has a value of a. This is an extremely trivial thing. Between 0 and 1, t, right? Well, if you take a look and multiply those two things together, you get a squared, right? You get a squared only where? Between 0 and 1. Follow me on that, class? All other values are 0. Forget about this uniform density thing. Really the expected value of A is just going to be, and here's what he's doing here. He's actually saying A squared is going to be the mean squared value of that thing. Do you all remember how to get the means, or the standard deviation? First, do you all agree that if it's A is uniform from minus 12 to 12, the average value is 0? Do you agree, class? If it's uniformly distributed. But the mean squared value, if it's uniform, if you remember that, is going to be the spread, which is going to be 24 squared, and then it's going to be over 2 times A. Anyway, for the uniform density, remember how to do this thing? And you end up getting it, and it's going to be over 12. So you get 12 squared. And let's see, it's 144. You divide it by 3. That would be, I believe that's right, 48. But this is only when T1 and T2 are between 0 and 1. Now there's 2 points to make. First, if you look at that, it's the expected value of a squared, because only when you're between T1 and T2 are from 0 to 1. But then the expected value of a squared you have to calculate. Follow me? And that expected value is going to be 48 if it's uniformly distributed. You remember doing this, right? I had it for, what was it, Gaussian, then uniform, and I forgot the other stuff you had to beat up. But basically, those two distributions.
I think it's b minus a squared over 12.
What?
B minus a squared over 12 is what it simplifies to for the uniform distributed to get that 48.
The upper minus the lower squared over 12?
It would be the lower, yeah, the upper minus the lower squared
So it's 24 squared?
over 12.
Is that right?
Yeah,
I don't know about that. Is that 48? It might be.
yeah, 576 over 12.
What's that?
576 over 12.
It is 48?
Mhm.
Okay. But I tell you one thing about this. When people don't realize this value has a randomness to it oftentimes. They're looking for a single value. It's not. It's a trivial example, but keep that in mind. So now, in general, this is the formal definition of autocorrelation. And this is something, when it's wide-sense stationary, please listen to me about this, or ergodic. I'm not going to parse the difference. Then the expected value, see, this is a time average here. The expected value here is going to be the same as the density function's average. With me on this? Now, that's the one big deal. If this is the case, for everything we care about it is, then you can just use the time variation of the autocorrelation to calculate this right here. And I'll tell you, that saves a lot of headaches. So here's an example, and y'all with me on this one, just bear with me. All right, now you'll notice we're going to assume we have a process x of t. Matter of fact, let me put this up on the board. I have a feeling this example really does a good job of showing what's going on. If we have let me give you the definition of autocorrelation that you're going to be using, because we're going to go down and identify things that can't be legitimate autocorrelation functions in some of the problems, but the real thing is you want a definition that works for any process we really care about as engineers. So here's the deal with this one. Our definition, assuming it's wide-sense stationary, we're going to get Rx of x of tau equal to the expected value of x of t times x of t plus tau. And that is, and we can use a time average. So if we can use a time average, we can take the integral of x of t times x of t plus tau, and we could integrate it. Really, it would be dt from minus infinity, or actually we can take from minus t to t, we can take 1 over 2t, and then, and I ran out of space, but if you take the limit of this as t goes to infinity, that would be the autocorrelation function. Doesn't mean a lot to you yet. Y'all follow me on this, class? We don't have to do density functions and do these, because we don't have them generally, but we have that information. Now, when we talk about autocorrelation, best way to see this in an example, this is the definition right here and here that we'll use all the time, or this. So now, if you have an autocorrelation function given to you, we're gonna assume that we have some x of t that's a process, a random process, which means it varies with t. It doesn't have just x and f of x involved here. It's gonna have some x as a function of t, and it's gonna vary. Then we can say here that we could get an autocorrelation function, Rx, and I'm just gonna leave it as x because it's the only function, Rx of tau. And for this one, in the example, he says it's e to the minus tau squared. Now that's an even function, has a peak value at tau equals 0. It has no sharp edges or anything like that, and it is a legitimate autocorrelation function. Then they say, got to process z of t, and say that's equal to x of t plus, and I'm trying to think of what he said in here. Yeah. Plus x, get a different marker. Plus x of t plus tau 1. Now tau 1 is assumed a constant. With me, class? And if you take a look at that, then if I wanted the actual autocorrelation of z of tau, that would be the expected value, follow notice, because here's where it gets interesting, of z of t times z of t plus, and this is the real value, tau, the variable. I'm just defining things in terms of z, not x. Now you take a look at that and expand it. So this is the expected value of, here it's going to be x of t plus x of t plus tau 1, and it's times x of t plus tau plus x of t plus tau 1. Y'all with me, class? And the only thing I'm doing there is just using a formal definition, but instead of x, I'm putting in z. Now if you multiply this out, this is my last point. So if you go down here and you take rz of tau, you're going to see the expected value right here. Those are all junk. There's one in here. Yeah, well, for now, that'll work. Anyway, if you look at this, we're going to have the expected value of x of t times x of t plus tau. And I can just keep going here. Y'all follow me in this class? It's going to have 4 terms right there. But what is this? When I take the expected value of just this. Anyone? That is the autocorrelation, by definition. Do you all see that? Just look at this. That's the definition. Over here, if I take the expected value of this times this, the first term, there would be 4 terms here. This would be the first term. Do you agree, class? You see how I would take this? I would have x times x of t plus tau. Then I'd have x of t plus tau 1 times x of t plus tau. Then I'd have x of t plus tau 1 times x of t plus tau 1. And then finally, I'm going to have the last term, x of t times x of t plus tau 1. Do you all follow me? There are 4 terms that you need the expected value of. But the definition of the autocorrelation function has to do with x of t and x of t plus some difference. Do you all follow me? Whatever the difference is what the correlation function right here is going to be based on. Can you all see it? So this right here, now there are 4 terms that I'm just trying to get to the bottom line here. When I look at r of z of tau, well, the expected value of this times this is just the definition of rx of tau. Now, if you take a look at the expected value of, take first inside, so this plus this, well, the difference is going to be what? It's just tau 1 minus tau. Do you all see that? Just subtract the second term from the first, you get tau 1 minus tau. So it would be plus rx of tau 1 minus tau. Remember, tau is the variable. Plus rx, and then for the outside, here, the argument is t times this, so it's going to be x of t times x of t plus tau 1. The difference is going to be tau plus tau 1. So here you're going to get rx of tau plus tau 1. And the final one, just watch this, z of t plus tau, I'm sorry, x of t plus tau 1 times x of t plus tau 1. The difference there is just equal to, if you look at from here to here, is just tau. So it goes back to plus rx of just tau. I guess my real point trying to show you this is, whenever you take any of these terms and multiply them by each other, whatever the difference in the arguments is, that's what rx is a function of. That's it. Follow me, class? And this is going to be the density function. I can go ahead and replace the rx of tau by that e to the minus tau squared. I know right now you're thinking about the quiz, so I'm going to stop there, but we're going to go from here, and I'm going to need you to do the problems this week, and because I'm going to go from here kind of quick into the spectral energy density, and that's the Fourier transform of this stuff. It gets kind of hairy. Let me go ahead and just give you